Hello everyone, I'm Juno from Seoul National University. Today, I'll talk about my work to you, specialized hardware architecture for accelerating inverted index search. This work is done with my colleagues at Seoul National University, Facebook, and Sungkyunan University. Search is definitely one of the most popular tasks using computers. It has been very important and it will continue to be one of the most important computer workflows. And search is a big data problem. The number of documents on the internet is one of the largest and fast increasing data. For example, the report indicates that Google currently indexes over tens of trillions of web documents. Considering these aspects of the search, it is obvious that we need to continue improving the performance and energy efficiency of the search. Specifically, to achieve this goal, it is very important to improve the efficiency of index navigation, which is the heart of the search operation. An index structure allows users to find specific data without exhaustively scanning all documents quickly. Among several index data structures, the inverted index data structure is the most widely used one for document searches. For example, many search engine libraries such as ASPLOS'20 and Elasticsearch utilizes the inverted index as their main index data structure. These search engine libraries are used to power many popular online services such as Twitter, Netflix, and Instagram. Below diagram shows the structure of the search operation. Once the user provides a query, the query is utilized to retrieve the portion of the index data. Once retrieved, various operations are performed on the retrieved index data to finally generate the set of documents that will be returned to the user. The below diagram shows the portion of the time spent on index operation during a search in Lucene. For different types of queries such as singleton, intersection, and union, through key operation, decompression, intersection and union, and scoring account for a large portion of the runtime. Here, the decompression operation mainly consists of bit operations that decompress the compressed index data structure. The intersection union performs set operation to identify the set of documents that are to be retrieved by this query. Finally, the scoring operation computes the search score for documents, which will be used to select the top search results. Unfortunately, conventional CPUs and GPUs are not the ideal choices for the search task. Key operations of the search that are briefly mentioned in the previous slide are simple operations involving a few amounts of computation. However, CPUs end up executing 70 to 100 instructions per document, which translates to the large energy consumption. Furthermore, the outlook of the core is not the best way to exploit the explicit memory level parallelism in search tasks. GPUs have their own issues too. First, it has a limited memory capacity that leads to frequent communication with the host CPU. Second, GPU's ability to perform a large number of computations is not beneficial for search operation, which involves very limited floating point computations. Finally, in many cases, GPU requires a large batch of queries to fully utilize its large amount of resources. To avoid the limitations of both CPU and GPU, we propose a specialized architecture for inverted index search, which greatly improves the performance and the energy efficiency of the search operation. Our work explores three key ideas to design the efficient hardware accelerator for inverted index search. First, we specialize the hardware so that it can overcome the limitations of general-purpose processors and exploit the large amount of memory-level parallelism in a search operation. Second, we co-design the indexing scheme and hardware accelerator to achieve further improvements in performance and compression rate. Finally, we support multiple levels of parallelism within the search operation through flexible interconnect. Specifically, our hardware can exploit both intra and inter-query parallelism. Our hardware achieves over 13 times query latency reduction, 5.4 times throughput improvement, and 18.6 times energy saving over high-end general-purpose processors. The search process consists of 5 steps. Our target is the compression in indexing scheme and other key operations. To achieve both low latency and high throughput for key operations, we co-design software indexing scheme and hardware accelerator. From now on, I will provide the software compression scheme for 2U. Before jumping into the compression scheme for 2U, I briefly introduce the inverted index structure. Suppose you have 3 documents. An inverted index is like a key-value data structure. The key is a term, and the value is the document IDs containing that term. To create an inverted index for each term, we need to record our document IDs containing that term. For example, for summer, which is the first term in document 0, we need to find all documents containing that term. In our example, document 0, 1, and 2 are stored as an integer in the table. To simplify the example, common words such as is, to, and in are excluded from the example. After indexing, we can get a complete inverted index. The inverted index allows you to quickly find a set of documents containing specific terms without having to scan every document, and document IDs are large and need to be compressed. 2U uses delta compression and bpacking compression. Delta compression stores the delta between 2 consecutive integers instead of the original values. This effectively reduces the range of total values. After delta compression, we apply bpacking to the L-delta list. Bpacking selects the largest value out of given values and converts the values using the smallest bit that can represent the largest value. In this example, we use 7 bits for these values. However, there is some inefficiency in applying these compression schemes directly to long lists. So long lists need to be divided into a set of blocks. Block partitioning can minimize storage overhead and exploit block-level parallelism. The following example shows the compression effect with or without partitioning. With partitioning, we can get a better compression ratio. Next, let's look at the partitioning scheme used in 2U. For partitioning schemes, it is divided into static and dynamic partitioning. Static partitioning uses a fixed block size, so it's easy to implement, but the compression ratio is low. Here is an example. With static partitioning, we have 2 blocks with 3 elements each. After partitioning and compression, the overall compressed block size is 42 bits. Dynamic partitioning uses a variable block size. Dynamic partitioning is a kind of an optimization problem whose object function is the total block size. We utilize the dynamic programming to handle this problem and derive the optimal block size. So, it's complex to implement, but we can get high compression ratio. In our example, the compressed size is smaller than the static partitioning. Therefore, we use dynamic partitioning and design the cost function of 2U for efficient compression. Now, let's talk about 2U architecture design. Before diving into 2U architecture design, I briefly introduce the overall search process via the inverted index. The user tries to find a document that contains both summer and vacation. First, the search engine finds the key value pairs that contain both terms in the inverted index. And then the engine restores the original document ID through decompression. Third, the engine finds common documents through the intersection. Fourth, the engine scores the relevance between query and candidate documents. Finally, the engine selects top K results from the candidate. After the search engine returns the document to the user. 2U architecture supports decompression, set operations, and scoring in this process. The overall architecture of 2U is as follows. 2U is an on-chip accelerator for supporting a search query. The host CPU offloads key operations to 2U, and 2U processes each query in two phases. First, in the scheduling phase, 2U schedules the query and configures the connection between block leader scheduler pair and 2U cores. In the computation phase, 2U fetches compressed blocks and operates decompression, set operations, and scoring. The host processor can utilize 2U with very simple intrinsic functions. Init needs to be invoked before the search to configure 2U and load the index file to non-cacheable memory. Then, the search function is invoked to send a query to 2U. All these units access memory through a Memory Access Interface or MAI, which is similar to MSHRs in general purpose processors memory system. 2U core operates key operations in the search. 2U core consists of decompression unit, scoring unit, and binary search unit. The compression unit decompresses the compressed block. Scoring unit calculates the BM25 score for each document. BM25 is a ranking model which is used by popular search engines. It computes a relevance score for each candidate document of a query by using term frequency and inverse document frequency. Binary search unit finds the candidate block for the first intersection. Let's use a singleton query example to show how 2U handles the search query. Suppose there are list L and else metadata lists. To simplify the example, we assume that our operations take a single cycle. In cycle 1, the block scheduler gets M0 metadata from memory. And at the next cycle, using the metadata, block leader gets the compressed block from memory. In cycle 3, the block scheduler schedules the first block to DCU0 and gets the second block metadata. In cycle 4, block leader gets the second compressed block. At the same time, DCU0 decompresses the first element in the first block. First, DCU decompresses 111. Then, DCU adds 7 to the previous value to restore the compressed value with delta compression. For the first element, the previous value is stored in metadata. In cycle 5, the block scheduler schedules the second block to DCU1, and 7 is sent to SU0 for scoring. At the same time, DCU0 decompresses 100. In cycle 6, DCU0 sends decompressed value to SU0, and DCU1 decompresses the compressed value. After scoring, document 7 with the score is stored in memory. In cycle 7, document 21 is sent to SU1 and DCU1 decompresses 11. And document 11 with the score is stored in memory after scoring. The remaining documents are stored in memory after scoring. 2U stops working when all documents have been processed. Finally, the top K selection is operated by the host program. Lastly, 2U can flexibly support both intra- and inter-query parallelism through the configurable interconnect between block leader scheduler pair and 2U cores. Here is an example. For intra-query parallelism, multiple 2U cores are connected to one block leader scheduler pair. Using multiple 2U cores for a single query can reduce single query latency. For inter-query parallelism, a single block leader scheduler pair is connected to a single 2U core. In this case, 2U processes multiple queries concurrently so that 2U can improve query throughput. We can apply different levels of parallelism to each query by setting the number of 2U cores controlled by a single block leader scheduler pair. We now move on to the evaluation. We use a cycloimage simulator integrated with DRAMSIM2 for 2U performance simulation. For power, energy, and area estimation, we designed 2U with CISO 3 and synthesized it with TSMC 40 nanometer standard cell library. To evaluate the effectiveness of 2U, we use Apache, which is a popular open source search engine library, and we uniformly sample 100 queries from track 2006 terabyte track. We use two datasets. One is CC News dataset, and the other is CoolWeb 12 dataset. We first compare single query latency across 4 different 2U settings. 2UX represents X2U cores connected to a single block leader and block scheduler. The leftmost bar represents Lucene with a single thread. 2U achieves over 13.8 times latency reduction on average. And we compare throughput improvement across 4 different 2U settings with 100 queries. 2UX represents the number of block leader and block scheduler pairs and the same number of 2U cores in a one-to-one mapping. The leftmost bar represents Lucene with multi-thread. 2U achieves over 5.4 times throughput improvement on average. 2U consumes about 1.1 watt power on average and consumes about 3.1 millimeter square area. In the figure below, we compare 2U8 settings with Lucene on the host. For 2U, top case selection is operated by the host CPU. As shown in the figure, 2U improves the energy efficiency by 18.6 times over the baseline system with a relatively small power and area cost. The figure shows that most of the energy in 2U is actually spent on top case selection on the host. To summarize, we present 2U to accelerate inverted index search, which is a time-consuming task due to a large number of documents. To address the inefficiency of search tasks on general-purpose processors, 2U utilizes specialized architecture, co-design of both indexing scheme and hardware accelerator, and flexible interconnect. With 2U, the system achieves 13.8 times query latency reduction, 5.4 times throughput improvement, and 18.6 times energy savings on the state-of-the-art search engine library. Thank you.